the evolution of air-launched precision munitions has reached a pivotal moment. Russia's new turbojet-powered glide bombs, such as the UMP-KPD and variants using compact Chinese turbojets, are transforming conventional dumb bombs into long-range, precision-guided strike weapons that threaten to reshape the dynamics of aerial warfare. At the heart of this transformation lies the integration of miniature turbojet engines with aerodynamic control surfaces and advanced guidance systems, allowing these bombs to travel distances exceeding 200 kilometers and strike targets with pinpoint accuracy. What sets turbojet glide bombs apart is their unique propulsion and design architecture. Unlike traditional gravity bombs or even unpowered glide bombs, which rely solely on the kinetic energy from release altitude and wing-borne lift to cover distance, turbojet-powered variants incorporate a small gas turbine engine. Once released from the carrier aircraft, the bomb deploys its wings and activates its turbojet, continuously generating thrust to prolong flight, maintain optimal speed, and overcome drag. This propulsion system fundamentally changes the operational parameters of glide bombs. It doubles or even triples range, allows for precise flight path control, and supports evasive maneuvers against enemy air defenses. Scientifically, the turbojet engine in these systems is a scaled-down, high-efficiency unit similar to those found in cruise missiles, but adapted for munitions applications. Fuel is stored in an integrated tank, and the engine is optimized for low-altitude, subsonic flight, often between 700 and 800 km/h. The powerplant keeps the bomb airborne for up to 10-15 minutes, making it possible to strike deep targets, circumvent terrain obstacles, and approach from unpredictable angles. The aerodynamic design, from variable-span wings to tail stabilizers, leverages computational fluid dynamics modeling to maximize glide ratio and stability, ensuring energy efficiency and controlled descent even at extended ranges. Guidance systems complement the propulsion, merging satellite navigation, GLONASS, GPS, IRNSS, with inertial measurement units, and in advanced variants, digital terrain mapping and electronic countermeasure modules. These allow the bomb to self-correct mid-flight, compensate for wind or jamming, and distinguish time-critical, moving, or fortified targets from decoys. The control module integrates microprocessors capable of complex path optimization and mode selection, delay fusing, impact detonation, or proximity airburst for diverse operational needs. As seen in Russia's use over Ukraine, the inclusion of turbojet propulsion has enabled attacks on command nodes, logistics centers, and bunker complexes formerly considered invulnerable to traditional bombing runs, and applications in SAAD, suppression of enemy air defense roles, have increased. For India, these technical advances are not mere patents or blueprints, they are strategic imperatives. India's indigenous glide bomb programs, such as the Gaurav and the SAAW Smart Anti-Airfield Weapon, have already proven formidable. Present glide bombs, powered only by aerodynamic lift after release, achieve ranges between 70 and 100 kilometers, and carry advanced guidance packages and warheads tailor-made for precision strikes on runways, bunkers, and hardened sites. The Gaurav, with its 1,000 kg payload and hybrid satellite inertial navigation, is capable of defeating a variety of targets well beyond enemy air defense reach. The SAAW, meanwhile, is lighter, but optimized for operational flexibility and integration with frontline fighters, from the Su-30 MKI to the Jaguar and Rafale. Yet the turbojet revolution offers India an exponential leap. DRDO has already launched a program to adapt turbojet propulsion onto SAAW-based platforms, working to convert these proven glide bombs into low-end cruise missiles with ranges exceeding 200 kilometers. The scientific challenges are substantial: miniaturizing a reliable gas turbine, balancing fuel efficiency with payload, ensuring in-flight stability at higher speeds, and integrating guidance resistant to enemy jamming. Recent advances in India's small turbine research, leveraging indigenous expertise in UAV propulsion, make this challenge achievable. The upgraded SAAW turbojet variant will measure roughly 2.5 meters in length, with additional internals for fuel storage and power management over extended trajectories. The revolutionary impact for Indian glide bombs is threefold. First, the standoff strike capability jumps dramatically. Indian bombers and fighters can launch precision strikes from well outside the effective range of enemy SAMs, minimizing platform exposure and attrition. Second, turbojet-powered glide bombs become multi-role tools for SCAD, strategic interdiction, and rapid response, able to penetrate layered defenses, hold mobile targets at risk, and overwhelm even hardened or deeply buried objectives with programmed trajectory shifts and delayed fusing. Third, these bomb systems are vastly more survivable against electronic warfare. Active navigation correction, increased maneuver flexibility, and shortened exposure time in hostile airspace all enhance mission assurance. Comparing the scientific principle, turbojet-powered glide bombs outclass unpowered variants by changing the fundamental energy equation. Instead of a flight profile determined by launch altitude and aerodynamic drag, the bomb now maintains altitude and velocity, adjusting thrust throughout its flight and even loitering if required. The control logic, leveraging machine learning and pre-programmed mission data, enables real-time path deviation in response to targets moving, defenses activating, or countermeasures being deployed. Indian scientists are integrating digital terrain contour matching and QR recognition fusing, leveraging artificial intelligence for target identification during approach. In operational terms, this technology allows a single fighter or bomber to carry more munitions, launch them at different intervals, and maximize surprise and effect on the target. The range increase also opens up new strategic planning. Indian strike platforms can threaten enemy infrastructure, air bases, command posts, and logistics nodes from inside Indian airspace, a true game changer for border operations or anti-access missions. When combined with real-time surveillance, networked ISR, and post-launch retargeting, these bombs morph into precision tools of operational art. Notably, turbojet glide bombs are significantly cheaper and easier to mass-produce than classic cruise missiles or hypersonic weapons, offering India a cost-effective way to saturate enemy defenses, conduct deep penetration strikes, and build inventory for rapid escalation. In terms of airframe integration, the modular nature of turbojet glide bomb kits makes them compatible with the existing bomb racks and pylons of India's Su-30 MKI, Jaguar, Rafale, and, with upgrades, the Tejas Mk1A. The ability to retrofit turbojet kits onto standard bombs means legacy stock can be transformed almost overnight. Scientifically, this transformation marks an inflection point for operator tactics. Indian pilots will be able to strike from unconventional headings, launch complex waypoint attacks, and program multi-bomb waves to arrive at a target moments apart, overwhelming defenders' response time. The potential for deep-fake decoy trajectories and coordinated seed missions turns every strike into a multi-dimensional contest where precision, flexibility, and timing matter more than raw payload. Internationally, India's ability to field turbojet-powered glide bombs will be closely watched, not just by adversaries, but also by strategic partners in air warfare technology. These systems could become export products, sharing lessons with other democracies facing similar threats. As seen in Ukraine, where Russian turbojet glide bombs have forced NATO planners to reevaluate air defense concepts, the proliferation of these munitions demands innovation in countermeasures, detection, and interception. In sum, turbojet glide bomb technology promises to revolutionize Indian glide bomb capabilities, marking the dawn of a new era in standoff precision strike. By integrating miniature turbine engines, advanced navigation suites, digital control systems, and flexible warheads, India can leapfrog legacy limitations. The scientific advances, propulsion, aerodynamics, active guidance, and modularity turn one-way gravity bombs into persistent, programmable, survivable strike leaders for 21st century conflict. This blend of science, engineering, and tactical vision is set to redefine not just India's strategic reach, but the way war is waged in contested aerospace environments worldwide.